In the previous video we looked at some of the introductory aspects about circular motion, so the fact that for uniform circular motion that the speed of the object is constant. We also dealt with the fact that the force acting in that situation is always perpendicular to its velocity. In this video we're going to have a little bit more of a look at that particular force, and you can see here that the title of that force is known as centripetal force, and we need to be a little bit more specific about some aspects about that force. So the force, as we've already said, is always perpendicular to the velocity, and that means that we can consider a few things about the acceleration of the object as well. One of the things I didn't specifically draw your attention to in the previous video is that the velocity is actually always going to be a tangent to the circle. So a tangent basically means that it touches the circle at a particular point. One of the things about a tangent is that if you draw a line from the center of the circle to the point where the object is positioned, then the angle that you'll find there is 90 degrees. And that then ties back into this idea of the force that we're dealing with. So that then means that the force is going to be always directed towards the center. So that's where this term centripetal force comes from, and we'll have a look at what that actually means if we sort of break the word down in its Latin roots. So that force, then, we can call it a centripetal force. So, as I said, that word centripetal comes from two Latin words. So the first part is that from the Latin we have that centrum means center, and the root of the second part of the word here is petere, which means seeking, or to seek. So basically what we're saying here is that when we're looking at the word centripetal, we're looking at something that's center seeking. So a centripetal force is a center seeking force, or in other words, it's directed towards the center of the motion. So the definition then of centripetal force, considering that's one of the dot points that we need to address, the definition then, so something that you should be able to state word for word, is that a centripetal force it is the force acting on an object that's either pushing it or pulling it. So it doesn't have to always be a pull. So if you think about something, whirling something on a string, that would be an example of pulling. Could be pushing it as well. So if you imagine, say, the walls of a ride that moves you around in a circle, so those walls would be pushing you back into the middle. So it's a force that pushes or pulls the object in towards the center of the motion. So there's the definition that you need to be able to state for centripetal force. Now we can tell then that there's an unbalanced force because the velocity is changing. So since it is an unbalanced force, we can apply Newton's second law. And we can identify that applying Newton's second law, we have the equation for Newton's second law. So I'll just jot down Newton 2 applies, and that means that we have the equation that F is equal to ma. Now, force and acceleration here being vectors, we can then identify also that the centripetal force is going to be equal to mass times centripetal acceleration. So Fc is the centripetal force, m is the mass, ac is the centripetal acceleration. So we need to now define what centripetal acceleration is. And as you might guess, considering that we're using the word centripetal, it's an acceleration that's directed towards the middle. But again, a definition that you could learn word for word is centripetal acceleration is defined as the acceleration experienced by an object moving in a circular path and that acceleration is also going to be directed towards the center of motion. So again, second definition there in this video, and really important to make sure that you can define these quantities in these terms that we're writing out. So if you are asked to define centripetal acceleration on an exam, you would pretty much need to state that word for word. Note here too that because we're dealing with Newton's second law, both the force and the acceleration are going to be in the same direction. We need to now have a look at how we can actually figure out what the force or the acceleration are based on the other quantities that we've already had a look at. So we're going to come back to the idea that acceleration is the rate of change of velocity. So while the speed isn't changing here, the velocity still is, given that the direction of the velocity changes. So we can deal with the change of direction in order to figure out something about the centripetal acceleration. Now in this situation we're going to start off with just a little bit of the motion of the object. So let's imagine we're starting there and it has a velocity. I'm going to call this velocity v1 because we're going to have a slight, at some later point in time, we're going to have a different velocity because the direction has changed, and that's going to be v2. So this object's going to have moved through some angle theta, and it's going to have travelled some distance along that circular path, and we'll call that distance s. I should also mention here that this derivation I'm about to go through is not something that you need to be able to reproduce yourselves. I just want to go through it so you're clear on where this next equation comes from, that we're not just making it up, and you can see how it is derived from the quantities that we know. So we have that equation there that the acceleration is the rate of change of velocity. So it's going to take a certain amount of time for that object to travel from one position to the next. So we'll note that that time is going to be delta t. If we look at the change in velocity, delta v, that's going to be the change v2 minus v1. Now, considering that these are vectors in two dimensions, it's going to be easier to consider that as a sum of two vectors, so v2 plus negative v1. So just taking that negative in with the term itself to make it a little bit easier to work with. So if we were to consider the velocities and the vectors that we're dealing with, so v2 would be in that direction, so that slightly angled one, and the vector negative v1 is going to be the same length but coming back down. So v1 was up, so negative v1 is going to be down. That then means that this little vector here is going to be delta v. Now just a little side note here, you should notice that the angle that that's directed on is basically sort of towards the center of the motion, so in this sort of direction, as the object moves from its original position where the velocity was v1 up to v2. You could show through geometry that this angle here is also going to be theta. So that's an important one that we'll come back to in a second. One of the other things to note on this diagram on the left, both of these sides here are going to be the radius r, and if you consider the smaller diagram over here that we've got of the vector addition, both of these vectors, both v2 and v1, have the same magnitude, so the magnitude there being v in each case. We have a situation that we can look at similar triangles. So considering similar triangles, and note that we're dealing with theta being a small angle. So the side delta V and the side S will approximate a straight line, not quite, but close enough. So if we look at the ratio of delta V over V, so just looking at the sizes of those two, that's going to be the same as the ratio of S over R. So just looking at these triangles again, basically what we're saying is that if we consider this triangle here, it's going to be much the same as this triangle here. So you can see that they've been rotated around, but the ratio of the sides will be the same because we have that the sides are both equal length for the longer two sides. So these two sides here being length R, these two sides here being length V, and we have a common angle being theta in both triangles. So we have that that ratio delta V on V is equal to S on R. Now the reason why we're writing it that way is that we also know another expression for the velocity. So we know that velocity is the distance over the time. The time here that we're dealing with is delta t. So we can say then that the value of S is going to be V delta t. So we're going to make that substitution into the line above. So we'll have that delta V on V is equal to V delta t on R. Now going through a couple of algebraic steps here, we're going to take the delta t to the over to the left, so we'll be left with delta V on delta t on this side, and that means we'll take this term of V up to the right hand side, so that's V multiplied by V. We're going to have then that's V squared on R. But we have already defined that this is actually what acceleration is, so delta V on delta t is our acceleration. So we can then write that AC is going to be equal to V squared on R. So that's an equation that's in the data booklet. So if we know what the speed of the object is, and we know its radius of motion, we can then figure out its centripetal acceleration. One last little step then, if we refer back to Newton's second law, where we're going to link force and acceleration, we can identify that the unbalanced force, as we said earlier, Fc is going to be equal to m times AC. We now know that the centripetal acceleration is V squared on R, so centripetal force is equal to m multiplied by V squared on R. In the data booklet, that equation's there as well. They have F net rather than Fc. Means the same thing, centripetal force being a net force that's acting on an object. It's just an unbalanced force directed towards the center of motion. So there's the two equations for centripetal acceleration and centripetal force. Let's have a quick look at an example question. So the example here that we're going to deal with is looking at calculating centripetal force. And the scenario that we're going to deal with is a car, and the mass of the car 1500 kilograms, traveling at 45 kilometers per hour, and it's traveling around a roundabout with a radius of 14 meters. So we'd have a circular path that the car's travelling around. Let's say it's positioned here on that circular path, and as it's travelling, you can see its tyres there. The direction that it's travelling in this case would be opposite the direction that I've indicated previously, so it's travelling that way. We know that its speed is 45 kilometers per hour, and we know that the radius of the motion that it's travelling is 14 meters. So if we go through and solve in that situation, the mass is 1500 kilograms, the radius is 14 meters, and the speed is 45 kilometers per hour. Now hopefully you've identified straight away that that needs to be converted to meters per second, and in order to do that you divide by 3.6, so go through the conversion of kilometres to metres and hours to seconds, and you'd find that that ends up being 12.5 metres per second. So the centripetal force then is going to be equal to mv squared on r. So that's substitute into that, we have 1500 multiplied by 12.5 squared divided by 14, which gives us a value of 16,471 newtons, and rounding that to the appropriate number of significant figures, we could write that as 16 kilonewtons. So there's a simple question involving calculating centripetal force. Obviously we can make that more complicated by considering the motion of the object in different ways. So instead of just stating what the radius is or what the period of the orbit or the speed, we might talk about how many revolutions per second an object is spinning, or various other measurements. We'll have a look at some of those sorts of questions in class, so that you've got a much more complete understanding of how to solve some of these sorts of problems.